Great. So today we're going to learn a technique, and it is a way of dealing with, just occurred to me that I'm not sure I know how to spell technique. Technique. Q-U-E? Oh, well, miracles never cease. I've given you guys a method to do integrals, and I gave it to you in such a way that I knew it would be challenging, but it would also be bulletproof. You could always use this method and it would work under all circumstances. It was not the most efficient way to do so. It was a way that I knew would always work, and I also knew from experience that you have to teach how to take an integral at a point in the school year where most of the students are terribly ill-equipped to be successful in that. Yeah, I have a few students who have been through calculus, but the vast majority of the students in the room are taking calculus for the first time or not taking it at all. And for those students, dealing with the level of difficulty of the content and having to add on top of that the possibility of doing this weird thing with an integral always made for a challenging bit of coursework. But what made it worse is that the students thought it was the calculus that was the challenge, and I'm here to tell you that it wasn't. The calculus was a portion of the problem. Setting up the calculus has always been the true challenge. So the first example I want to look at is a two-dimensional disk for a minute. Okay, just a two-dimensional disk. And in this example, we're just talking about this idea of taking a sum. And I'm not doing anything more. I'm not talking about charge density. I'm not talking about anything else. I just want to talk about what it means to take a sum. Does everybody understand? Because that's what an integral is about. So I'm going to talk about the area of a disk. Okay, that's all I'm going to bring up for a moment. If you want to find the area of a disk, we've done this problem before. But ultimately, the calculation of area could be expressed as the integral of dA, right? It's summing up all of the pieces of area of the object over the entire object. If you do so, you'll have the area of the object. Now, when I taught you to do this, what I suggested you do was consider first if there's a certain numbering system that would work best for your particular shape. Should you use a Cartesian set of numbers or a polar set of numbers? We were only dealing with 1- and 2-dimensional problems at the time. A problem like this lends itself to polar. So I recommended, okay, if you're using polar numbers, bless you, then set up a coordinate system that you could use as reference, because you're going to need reference. If you're going to try and add up all of the pieces of area, then you need a way to count each piece of area. So I would say to you guys, draw a square somewhere in the object, put in something to apply reference to the object itself to give you an idea of what you're going to use as a reference point. So I'd always usually say, at least draw in something that you could call a 0, and then how are you going to measure where this square is? So I said, find a way to point to the first corner of the square. And so I'd say, you draw a line in from, say, here to here to get us to that first corner of the square. And start making placeholders that could be used to help identify where this location is. For example, I'm going to turn an angle theta to get over here, and I'm going to go up a distance r. All sound familiar? We've done this before, right? And then I would say define the size of this shape by using your placeholders to help you identify the lengths that you could use to calculate area. So I probably would have zoomed in and said, well, this is going to be just a little more in the direction of r, so we'd call that dr. And then this is an arc length swept out by r if you moved it a little more in the direction of theta. So I would have said that this is r d theta. And then we would have talked about the idea that, does this naming convention allow you to name every single square that's on the disk. Can you start with squares that are along the 0 degree mark and get to all the squares all the way around till we get to the 2 pi mark? And, we've done this before. This is not a big surprise. We would then take this and say, all right, starting with here, the area of this small box, dA, would be its length times its width, or dr times rd theta. For those of you who kind of understood this, for the most part, you realize that every single integral that dealt with area of a polar surface, you had this dr times rd theta component as a part of your integration. So then we would indicate that the area is going to be the integral of dr times rd theta. Realizing that there's 2 of these, we would double the integral to make sure we summed over both of our values. We would rearrange it, and I would probably do some gross language about making sure that r and theta are not necessarily related, that you have for every r you can map the entire circle of theta, or for every theta you can map all of the r's. Language that for most of you went way over your heads, but the idea being that is your shape symmetrical enough where for every single angle you can go from 0 to the radius of your circle? And in this case, yes, because we're always dealing with these symmetrical kind of shaped objects. If that were true, then you can bring all the pieces that have r together with dr and all the pieces that had d theta together with d theta, and then you would set your limits. I need to go around the entire circle, and I need to go from the inside to the outside. And that's where you got your 1/2 r squared times 2 pi. 1/2 r squared times 2 pi, which gave you the obvious pi r squared. Right. This is how we did it before. This is a lot harder to do if your system is 3-dimensional. Because if your system is 3-dimensional, then it's no longer a small square of area, but a cube of volume, which means I would have to project this in the third degree and deal with probably some other way of measuring 3-dimensional coordinates. Now, we've not talked about the ways to measure 3-dimensional coordinates, of which there are, as you can probably imagine, 3. So, how many of you are familiar with 3-dimensional coordinate systems? You are all familiar with one of them because all of you know X, Y, and Z. So the fact that you didn't all raise your hands either means you're not paying attention or you don't understand the question. So let me try that again. Are you familiar with 3-dimensional coordinate systems? Okay, good. I'm just trying to make sure we're all paying attention and not dreaming of Taylor Swift. So X, Y, and Z is a way to deal with a 3-dimensional object. It would be terrible to deal with a sphere using X, Y, and Z. Because what are your limits going to be for a sphere in the X direction, Y direction, and Z direction? They're different depending on... That'd be like trying to identify all the squares of a circle depending on using nothing but X and Y. How would you set your limits? Well, you could do it. I could redraw this and say, okay, my square is this, and I will put in a X coordinate system and a Y coordinate system. We'll do it this way. But that means, for this point, I'm going to have X in that direction and Y in that direction. This is going to be dy, and this is going to be dx, and my area is going to be dx times dy. But how do you set limits for this? Because you can't set the limits from 0 to r in both directions or you'd get a square. What I mean is, right now, if I say this is x, this distance right here, does y go from 0 all the way to r when it has to stop here? Or is that less than r here? It's got to be less than r. Also, if I go out to here, if I want to identify, say, this square, how do I tell the calculus not to go from here all the way to here? How do I tell it to stop here? Every single x has a different range for y. I would have to find a relationship between x and y and use that in my formula. Now we have a relationship for x and y. Right? That's the equation of a circle. You could do it. You could solve this for y and put the entire thing in terms of x so you would know the limits for x for every y. But you see that that's going to be a much harder process, which is why you pick a coordinate system that kind of matches the shape of your object so you're not bound by those limitations. Now, there are three ways to do three-dimensional coordinates. There's x, y, and z. That's still Cartesian. There's what's called cylindrical, which is like polar notation with a z-axis. And then there's spherical. So you can imagine that having to do a double integral to figure out the area of the disk. So you could ask, well, why did you teach us this method if there was an easier method? Well, there are some reasons why this method is better. One reason is, what if your charge distribution is half charge on one side of one type and half charge on the other side of a different type? You couldn't use concentric rings then. You'd have to do something like this. But moreover, because here we were doing it holistically, all we need to know is the area of a square, length times width. So we didn't have to know the circumference of a circle to be able to get the area here. For any point, x, y, and z will point to that location. The polar version of this is r, theta, and z. That means if I want to identify a point here in space, right there, I would say, okay, I'm starting here. I'm going to go out that far. I'm going to go over a little bit, and then I'm going to straight up from there. That's where my point is. That's how cylindrical would do it. If I want to do spherical, well, I say that my starting point is, say, straight up, and I'm going to go, that's 0 degrees. I'm going to come down, and I'm going to turn a little bit, and then I'm going to go out from the center till I reach that point. So spherical uses a pointer vector like polar, and it uses two angles to try and figure out where your point is in space. These are the three different kinds. This is harder than it seems, in that once you realize how to do this, then you still have to figure out how to define the cube. So here, of course, it would be dx times dy times dz. That would be our d volume. This will be r dr d theta dz. That would be used to find our volume. But this one's going to be, we use rho for spherical. Rho squared d rho d theta d whatever the heck that is phi. And this is how you find a volume for spherical coordinates. It's just more than we're going to do. There's a shortcut. There's a simplification. And I want to teach you the simplification because it tends to make these easier. And I want to teach you that simplification here by redoing the circle again, right? Redoing the disk. Because I think the disk is so similar to the sphere, it'll help you understand. And obviously, they want you to be able to do this on the exam because they've given a problem where this is the only way to get your answer on the exam unless you use the spherical coordinate system I just described. Now, this is a very common shortcut. It's a very common technique. So I'm not teaching you anything that's secret. What it's really about is remembering that an integral is a sum and will allow you to sum anything as long as you can define it. So I can take something like this, a disk, and consider the fact that I could build a disk as a sum of individual rings. Right? You can imagine that, right? That the disk could be made up of any number of concentric rings. I don't know why my little dot won't go to the middle. Put the little dot in the middle. There we go. Right. Now, there's an advantage to doing this, and there's a disadvantage to doing this. the advantage is that this works really great in situations in which you have a symmetry that can be used to your advantage. Obviously, a circle can be considered a bunch of different concentric rings. If you have a system in which your symmetry is not as easy to exploit, you may not be able to do this. But this is why you've noticed on our exam we have lots of spheres, things like that. That's because they want to use this kind of symmetry. Now, just like before, we're going to try and find a way to define each of the rings. And that part shouldn't be too hard. But the difference here is that rather than having to pick a spot for the angle, I'm going to say that all the rings are concentric. Now I'm trying to find an area. So how would I consider a piece of area of the ring? Well, what I do is I assume that the ring has a circumference equal to, of course, 2 pi, in this case, r. But then I also say to myself that each ring do this just right. Each ring has a thickness, dr, a little more in the r direction. And that the area of the ring would be the space between these two. So I would take this circumference and multiply by dr, and we say that the entire ring is that amount of area. The circumference times how thick the ring is. You follow what I'm trying to say? Imagine right now, most all of you have something circular. If you were to unscrew the cap of your water bottle or the cap of your or if you just had like I have a cup, this is the thickness of the ring. Now, multiplying a circumference by 2r isn't exactly the amount of thickness it would be. I'm sorry, exactly the amount of area it would be. We know that the outer radius and the inner radius are slightly different, so I'm a little bit off. But remember, through the magic of calculus, dr is so small that this still works out to be an area. If you don't believe me, let's look at it. A lot of you have asked this question in the past, and this is why it works this way. dA is going to be 2 pi r dr. I want to add up every ring from the very inside to the very outside. So I'm going to conduct this integral. Well, to conduct this integral, I'll take the 2 pi out front, and I'm just integrating r dr from 0 to capital R. The integral of r, of course, is 1/2 r squared, evaluated from 0 to r. So plug in my limits, and I get pi r squared. Now, I'd argue that's a lot easier than what we just did over. This is how we get around dealing with problems in which our system is spherical. If our system is spherical and we're not given the tools to do a spherical integral, is there a way to do an integral for a sphere that uses the same kind of symmetry? And the answer is, of course there is. You'll notice here, the only way we were able to figure out the area of a disk is if we knew the circumference of a circle. Like we already had to have one formula in order to get the other formula. We didn't need, here we did. Imagine this time that this is not a flat disk, but is a sphere. And let's say that we want to figure out what an expression is for the volume of a sphere. Now, of course, this requires that we know something else about the sphere. So in this circumstance, I'm going to do the same kind of thing. I'm going to choose a smaller hollow sphere that is concentric with this sphere. And I'm going to say that, well, this sphere has radius r and has a surface area of 4 pi r squared because it's a sphere. Now again, I'm trying to make this part very painfully clear. This only works because I know the surface area of a sphere. If I didn't know the surface area of a sphere, this wouldn't work, and I'd have to use a small cube. So you have to already know something to use this technique. Yes, Oliver?
But I mean, don't you also have to know how to measure arc length through the traditional method?
I don't think so. Not to just find the volume of a sphere. Because
you're saying that we have to know how to
record any of that. Sorry, guys, I didn't record that for all of you listening at home, which is probably none of you. But I got into an altercation, and I didn't want to record that for fear that, I don't know, maybe somebody at the state would hear me being mean to a kid and I'll lose my job. Or because people are going to train some voice AI on my voice and make me say mean things. I really don't know. I should just stop posting videos altogether. But I want you guys at home to realize we just took the thickness of the blue sphere by multiplying 4 pi r squared by dr, and then we integrated it and got 4/3 pi r cubed. But the big takeaway is, okay, Mr. Shelton, you did all that work, and all you did was tell me what I already knew, the volume of a sphere and the area of a disk. Why'd you bother? Because you weren't supposed to find the volume of a sphere. What were you supposed to find? The charge of a spherical-like object, right? So we had a spherical shell that had an inner radius and an outer radius. And more importantly, because that wouldn't have been such a big deal, you could just have found the big volume and subtract the inner volume, and you would have gotten the charge, but the charge density was non-uniform, right? We had a charge density, which I'm going to use, I think they used rho for the charge density. We had a charge density that was some whack kind of thing. Let me put it in here so we have it. It was some expression. I don't care about the number part, obviously, but I do care about finishing before the bell rings. So that's going to be just B over R. So it was some constant divided by the radius. So this suggests, of course, that the charge density is getting smaller and smaller as we get to the outer edge. Now, if I wanted to figure out the total charge is going to be broken up into small pieces of charge. And each piece of charge has to be the charge density times the piece of volume. Well, this integral will give me the total charge. But to do this integral, I need a method that will work in 3 dimensions. Do you think I could use concentric spheres to do this integral? The only way this works is if each concentric sphere has the same charge density. That's the hard part to recognize here. The distribution of charge has to be such that, this is what's worth writing down, each sphere has the same charge density, so that the charge density all along this sphere has to be the same amount. This will only work if your charge density has spherical symmetry. If it's not symmetrical, if there's more charge, more gooey, chargy stuff on one side than the other, this doesn't work. But if the entire sphere, if that entire hollow sphere is all the same charge density, then you can do this. This one, I'll point out, the charge density is based on how far away you are from the center. So it works. So I'm going to replace my dV not with some complicated single little cube, but with 4 pi r squared dr. So again, I'm replacing dV with the volume of the shell that I'm using for one of my little spheres, and then I'm going to add up all of the spheres. Does that make sense? So this part is the dV. Right? This is how big the sphere is. This is how thick the sphere is. And that's a volume. So drop in my expression for the charge density, B over R times 4 pi r squared dr. And now integrate. In this case, in this problem, we had to integrate from 0.03 to 0.05. And sorry, I forgot to put that in there. That's dq. So b is a constant, 4 is a constant, pi is a constant. So 4 pi b integral 0.03 to 0.05 of 4 pi, oops, not 4 pi, what am I doing? Of just what? R squared times 1 over r is just r dr. That's pretty straightforward, isn't it? This integral, it's going to be 1/2 r squared. So 4 pi times b times 1/2 r squared evaluated from 0.03 to 0.05. This is how question A was done. You guys can throw all the stuff with your calculator in there. You would need to know what the value was for B, and this is the clincher. The value for B was 1.6 times 10 to the negative 6th coulombs per meter squared. So if you understand why it's important to look at the units, your expression that you get for calculating Q had to be in terms of meters squared, so you'd be left with coulombs. So when you work it all out, you get Q equals 2 pi times 1.6 times 10 to the negative 6 coulomb per meter squared times 0.05 meters squared minus 0.03 squared meters squared. That's a minus sign. Doesn't look like it, but it is. That's how you get the numerical answer for this, which ends up being, I can't remember what it is. Small, but not particularly interesting either. I think it's like 1.8 times 10 to the negative 8 or something. I can't remember.
Is that what it was?
So, now I'd love to tell you that this is, this was easy and you'll remember it. I don't know. I'll tell you this. When I did the problem, took me about, I knew how to do this technique. I was versed in it. And I looked at trying to use another technique first, but this is the only way I could think of to do this problem. It took me about 2.5, 3 minutes to come up with the technique and then execute it. And then I executed it twice because I wanted to make sure my numbers are right. Something felt funny about the value I got for charge. But I think this is the way to do it. And it's not particularly easy, clearly, but it's not terrible either. To be honest, this only works in like 3 or 4 circumstances. And you've seen 2 of them. It works for finding the area of a disk or things related to the area of a disk. So charge of a disk, if you're given a non-uniform charge density of a disk, that would work. It works in this case because of the sphere. This has been on the exam before. It's been on the exam multiple times. But when it's on the exam, it's this exact problem. It's exactly this. So the only difference between this problem and every other version I've seen of it on the exam is if there's a hole in the middle or not. The funny thing is, I thought I gave you one of these in your homework, but nobody ever asked about it. What's that?
It was problem 2.
So, I believe it or not, in my head, I thought I was giving you like the reference problem before it was going to show up on the exam. But we didn't do it. We probably should have. But no one asked about it when we went over homework.